as several speakers have alluded to, it has become a commonplace in the past few decades in the literature on foundations of statistical mechanics that there's a schism, a rivalry. It's hard. There's no consensus on exactly how to characterize it, but it has been called a schism in the foundations of statistical mechanics between Boltzmannian and Gibbsian approaches. And as far as I can tell, this idea of this kind of rival approaches really started to come to fore in the literature in the late 1990s and early 2000s, partly as a result of the polemics of the Rutgerian Boltzmannians for, Joel Leibovitz and Shelley Goldstein. Craig Callender was a graduate student at Rutgers at the time, and I was really struck by, in Bicin's slide, list of Boltzmannians, how geographically concentrated that was. Because if I'm remembering right, you had Goldstein, Albert, Callender, and Maudlin, and was that everyone on your list? On Bicin's list, you had this list of
Cited Lavis.
And Lavis too? Okay. Right. Yeah, and
Brickmont.
Yeah, and Brickmont. Brickmont was a participant at the time. Of course, he's a very good friend of Shelley Goldstein's. Right?
Yeah.
And one thing that's been happening in recent years is people have been there have been some people, including me and David Albert, saying we actually don't think in actual statistical mechanics practice there are these rival approaches. David has argued that there's what's called Boltzmannian techniques are a special case. Apparently, I've said that they were complementary. I'm assuming that was a quote. And that sounds like the sort of thing I would say. And there's been, questions in the literature about exactly what the distinction is. Roman and Charlotte wrote this paper. Could someone please tell me what Gibbsian statistical mechanics says? And so the question for the round table, I'd like to hear from everyone, do you think that there is, there are rival approaches to statistical mechanics? And if so, if not, why not? And if so, what do you take the nature of the disagreement to be? And maybe I'll just start at that end and we can pass the mic down this way. Okay, or we start this end and pass the mic around us.
Yeah. Okay, so I think there is a substantive real dispute here. I think it's a philosophical dispute inside the philosophy of the foundations of statistical mechanics. And it's non-illusory and it's somewhat important. And the way I'd characterize it is there's a specific position which was labeled Boltzmannian without prejudice to whether that's correct. That's historically salient. The positive aspects of that position, I would say, are something like equilibrium is characterized by entrance to the largest macrostate. The explanation of equilibration is very tied to the size of that macrostate. Incidentally, this isn't to say that everyone who said they're Boltzmannian adopts that position. Charlotte and Roman's position is different, but it's to pick up this distinctive position I want to comment on. The entropy is the log, the thermodynamic entropy is the log of the volume of that equilibrium macrostate, and the thermodynamics is inherently macroscopic and approximate. And equally important, it comes with a critical component that it has a bunch of thou shalt not. Thou shalt not represent systems in statistical mechanics or thermodynamics by probability distributions. Thou shalt not appeal to dynamical notions like mixing or chaos to explain equilibration. Thou shalt not use the Gibbs entropy as a thermodynamic entropy. Thou shalt not use supposed thermodynamics as any connection to information. So just to quickly say, as a demonstration from Shelley's very widely cited 2001 paper on this, the abstract says, most 20th century innovations, such as the identification of a state of a physical system with a probability distribution on its phase space, of its thermodynamic entropy of the Gibbs entropy of rho, and the invocation of the notions of ergodicity and mixing for the justification of foundations of statistical mechanics, are thoroughly misguided. And there's a large panel, so I won't quote more parts of it, but the paper goes on and on and on and on. So this is a very substantive intervention not just in the metaphysics of statistical mechanics, but in the substantive scientific practice of statistical mechanics. It's interesting, it's well motivated, and in my view, it is completely wrong. And it is important that it's completely wrong, because I think were statistical mechanics to adopt it, it would paralyze the subject in large areas of it. So I think it's quite an important question. I'm not intending that, but it's an important question in philosophy of statistical mechanics, whether this form of criticism that has been levied at mainstream statistical mechanics by a very small group of physicists and a much larger group of philosophers as merit is correct. I don't think that should be diffused away. And if it's the case that the advocates of that position around the turn of the millennium now think something different, that's fine, but that original position is still in the literature and highly influential, and it's relevant to assess it.
Yeah. I agree with everything that David just said. And if you ask me about the relation between these two positions, I think the most salient thing that strikes me is that in the Boltzmannian approach, it seems to be crucial that we're dealing with systems that have a very large number of microconstituents. So they all, and this is not just true for Boltzmann's earlier work, it's definitely also true for his combinatorial argument, which is the basis of your Boltzmannian approach, because he calculates the volumes of all these macro states, and that depends heavily on using Stirling approximations, which are justifiable if the number n is large, and all the other numbers as well. And it also is only under that assumption that one of these macro states is going to be overwhelmingly large to dominate most of this phase space. So if you were to consider a system with just a small number of constituents, all of these tools are not applicable. In contrast, in the Gibbsian approach, most of his work, as I mentioned before, most of the chapters of his book are just about the Hamiltonian on a particular phase space. It's only in the last chapter that he starts to talk about systems composed of molecules. And even then, there is no inhibition against considering small systems with just a few molecules. That's still a Hamiltonian system. You can still talk about the the canonical and the microcanonical ensemble, and you can apply all the results that Gibbs has given you in order to find thermodynamical analogs of that. So that's a limitation of the Boltzmann approach that you don't have in the Gibbsian approach. Whether that's a good thing or a bad thing, I don't know. We might differ on that, but it's a salient difference. A second thing that I wanted to say is that there may be more common ground than is commonly perceived. So once again, in the Boltzmannian approach, the first thing you have to do is to take a phase space and then carve it up into a partition of macro states. Now, the recipe for doing that is somewhat flexible. If you heard Charlotte say yesterday, you have to choose a set of macro variables, and then the macro states are characterized by the condition that the macro variables take on certain values on that set. So that's very flexible, which is fine. But in Gibbs's approach, once we talk about systems consisting of molecules, you actually find a similar technique. because he then discusses the question of whether all these constituents, these molecules, are entirely similar. And if they're entirely similar, one can consider permutations on a microstate and consider the equivalence class of all these under all these permutations, and that leads to a partition of phase space by these equivalence classes. And if you quotient these out, you get a macroscopic description, which Gibbs calls, I think, the specific phase, in contrast to the generic phase. And I think that in the Boltzmannian approach, although it seems like this carving up into macro states is entirely up to the choice of these macro variables, I think permutations are probably the minimum requirement that you have to consider in order to call a certain function a macro variable. That is to say, if you just permute two particles, then typically all the macroscopically relevant variables take the same value. There's nothing observable that changes if you just do permute two electrons or two classical particles or two quantum particles. So that these macro states should be invariant on the permutations, I think, is probably one of the first conditions you would have to think of. And that, in that sense, the Gibbsian partition, which leads to the specific phase, is going to be identical to the partition that Boltzmann would use if we also use the permutation invariance to pick out our macro variables. Of course, it's just a minimum requirement. There can be other considerations to pick a finer finer partition, but that's sort of minimum, I would think. And in that respect, I agree. And if you could also look at the BBKGY approach that Charlotte talked about yesterday, this also takes explicit account of the permutation invariance by, in this case, taking a symmetric probability distribution over phase space. But that leads to the same result. And then you can consider just the marginals of that probability distribution. And in typical cases, you would have the one particle distributions, the two particle distributions, maybe the three particle distributions. There were very few quantities in physics that would have to depend on more than two particles, like the interaction potential typically. So there was a reasonable expectation that if you know the first few members of the BBKGY hierarchy, you will have a lot of information about the system. And of course, you're not done there, but it shows you that there is some consilience or some overlap between the Boltzmannian and the Gibbsian approach in many actual applications. I think that's roughly what I would want to say as a starter.
Yeah. So my short answer to Wayne's question is I don't think Boltzmannian and Gibbsian approaches are opposed to each other, but I do think there's still disagreements roughly tracked by the two approaches in the way that the debate can be reframed as maybe David's position, the Boltzmannian approach is a special case, or the Boltzmannian is somehow more fundamental. How exactly should we understand probability here? Can we tell a conceptually clear or even ontological story about probability distributions? How we should understand statistical mechanics? Is it like a special science, or is it more fundamental theory? So I think there are a lot of open questions in the way that there are going to be disagreements, even though they may not be necessarily tracked by the distinction, but probably roughly along these, that I think still worth diving into.
Okay, so I guess I should maybe speak up a bit more for Boltzmannians. I am a Boltzmannian, and I think I'm a real Boltzmannian. I don't know whether I'm a fake Boltzmannian or not, but you can let me know. But I think, as many of you have hinted, there are different approaches, even within Boltzmann system mechanics, because tolerance of probability, I differ. I like probabilities, but I have interpretation probability that's somewhat different from other people's interpretations. I'm okay with both Humean and non-Humean probabilities, which might explain why I'm okay better with probability than others. Whereas for people who don't like humanism, but I'm not non-Humean, but I think humanism makes sense. So you can use it to understand certain ways to think about physics, system mechanics, quantum mechanics. Then the difference between Gibbsian and Boltzmann system mechanics might just be more, you can translate back and forth between them. I guess the main difference between them would be how to define entropy, how to think about approach to equilibrium from non-equilibrium. So you have coarse-grained Von entropy versus just the Boltzmann entropy, or the Gibbsian entropy, coarse-grained, and the just a classical Boltzmann entropy. It seems like in the end they give rise to similar kind of effective dynamics of how macro states evolve or how product distribution evolve. But I think for some Boltzmannians, it's important to frame everything in terms of typicality measures. And then in that case, you can have some ways to think about coarse-grained product distributions over phase space or Hilbert space. And you can use a single distribution as a representer to denote that product distribution, denote the typicality distribution, but typicality is much more coarse-grained. So to get single-shot probabilities from this quotient distribution, you have to do some work to think about long-round frequencies of some patterns or many collection of subsystems. So I guess it really comes down to the foundation of probability in the end. I mean, if one accepts that the definition of entropy can be translated between Gibbsian and Boltzmann approaches. Thank you. And
yes, how I like to think about this is in terms that maybe the distinction is not between two different and incompatible foundations of statistical mechanics, of a theory, but about two different philosophical projects, where one of them is interested more or less in recovering thermodynamics for systems with many degrees of freedom. One may be interested within one of these projects in recovering an error of time that is independent of any external system, that is independent of any particular or any, some may say, subjective coarse graining or forgetting, or external agents or external descriptions that involve some restricted access. And recovering in this sense also equilibration and irreversibility for isolated systems, whereas there may be also another philosophical project that is more concerned about extending the tools, for example, of thermodynamics to other regimes, to understanding, to giving a theoretical framework that can accommodate fluctuations, that is fine with incorporating resource theoretical techniques, information theoretical techniques, probabilities, and that aims to cover a wider regime and apply these techniques to a wider regime. So in this sense, I see it not as necessarily as two different foundations or one theory, but or two different radically different interpretations of statistical mechanics that are incompatible between them, but in terms of two different philosophical projects that may not a philosophical project that may or may not be totally relevant for the actual practice of physicists.
Right. Oh, right. Yeah. So I guess my view it starts from maybe more epistemologically, like instead of just looking at of physics and checking where our safe points are. Looking at I think of it as like the starting point is thermodynamics, right? And it's equilibrium thermodynamics. And then we have Maxwell found the Maxwell-Boltzmann distribution, and then and Boltzmann together. They found it. And now we ask, okay, how can we go further? Now we go further from that, and everything's still fine and dandy. It's all connected back to thermodynamics. And now Boltzmann provides a simple model that provides an explanation, micro explanation of this sort of statistical thermodynamic behavior, right? Fine. And then as Bixin showed helpfully that the Gibbs approach is equivalent to the Boltzmann approach in this kind of a regime where it's a large number of particles, non-interacting, weakly interacting situations. That's totally fine, right? So it's equivalent in that regime. And then I think, well, in that case, in this regime where we know thermodynamics work and we can explain it either in the Gibbs way or the Boltzmann way, then it seems like both of them are as real as they get in that regime, right? In that context, maybe similar to what Jos was saying, in that they have like lots of consilience there. Then the question is, okay, can I go further than that? In other contexts, can I also generalize the Boltzmann picture? Can I generalize the Gibbs picture? Then it seems like that here's where the sort of breakdown of consilience happens. There's this divergence when it comes to, say, tracking macroscopic states. Like if I knew the macroscopic parameters like temperature, heat, temperature, pressure, volume, so on, what can I know about the macro state and what about the distributions, right? And then Gibbs tells us a lot about that. And then I guess, okay, given that, can I get a micro sort of physical explanation of those distributions of a single microstate in terms of those distributions? And then except in the simple case, and maybe I'm not sure other exotic cases, I'm not sure how Boltzmann can do that, the Boltzmannian picture. Then in that case, it's just like, there's no question about whether we should be Boltzmannian or Gibbsian, right? Because it's just nothing to compare, right, in those contexts. Doesn't mean that in the equilibrium context, we can't think of the Boltzmannian picture as correct, or maybe in the cases where they work, but that more work has to be done. And of course, Craig's complaint is always that, well, you know, that's because no one works on it. Like if more people worked on the Boltzmannian approach, then maybe we could have gone further. Similar.
In that vein theory, though.
Yeah, I was gonna say it's similar to Bohm, right? If only more people worked on it, but then sure, yeah, then we have to work on it. And I guess maybe the people who complain the most about this, they are, of course, and then they should be working more on it. And but until then, it's hard for me to say, well, you know, one is better than the other. In some contexts, it's just no competition at all, right? Of course, like the Boltzmann picture, instead of generalizing tracking of macro states and different types of distributions, now they want to say, okay, can I generalize the microontology, right? In the dilute gas cases, I have this microstate, and I want to generalize to, say, microstate in other contexts. Well, it turns out it's not very easy to do, right? And it's very difficult to work from the ground up. And in the cases we can, that's nice, but in the cases we can't, then I don't even know how to begin comparing Gibbs versus Boltzmann. So maybe I'm just very contextualist in that way. I'm like, well, there are contexts in which you can say with certainty or like confidence that Boltzmann is as good as the Gibbs picture. But in so many other contexts which makes contact with the real world, the empirical setting, there just is not much to say about the Boltzmann picture for now anyway. And it's an open project. I'm not saying this is a close and shut case, but it's like, yeah, more work needs to be done. And then physics is all about an ongoing process, and we are doing the work. Yeah.
Okay, moving to our online panelists. Charlotte, we're going to go next.
Sure. Thanks. I hope you can hear me well. I'm in agreement with a lot that has been said. I mean, about the two frameworks, I tried to present the basics of both frameworks in my talk yesterday. So I see Boltzmann really as, we had this picture of dividing up state space or phase space into different macro regions. And then you get equilibrium as the largest macro state, or the state the system spends most of its time in, and you can consider microstates and how they evolve into the equilibrium region. And Gibbs is, of course, about an ensemble, and equilibrium very differently an ensemble property. I mean, this is how and your phase averaging that is usually done, not always, but usually, and you have the Gibbs entropy, etc. So these are the basics of the two frameworks, I think. And then I'm in agreement. I mean, I wouldn't say from the outset that these frameworks are inconsistent or are or cannot be applied together. I think this will these are really fruitful questions for further research to look at the situations. I mean, I think there are many situations where they are applied together, and where one can probably say they can be consistently applied, or even make sense that both can be applied. But yeah, it would be interesting to analyze these situations in more detail. But yeah, what Jos has said about how they can be applied together, I think I'm very much in agreement with that. But I think the picture is probably mixed. I mean, this is further research, but in some cases, it might be that we only do Boltzmann, or that we only do Gibbs, or that you know that with Roman we have that paper out there where we compare the phase averaging values. So with the Boltzmann equilibrium value, so you compare the Boltzmann and equilibrium value, the value of the system in equilibrium, with phase averages in Gibbs and statistical mechanics. And as you all know, in many cases, they give you the same results, but not in all. There are some cases, at least, where you don't get the same results. And then as the question, what do you say about that? You might say, well, the Gibbsian shouldn't do phase averaging in that case, or you might say that the frameworks are, in this case, not consistent or give you different results. I don't want to take side. I'm not really interested to say the one or the other. That is just the question, what would you do in these situations? But to summarize, I think there were some situations, I think, where they certainly both are applied, are perfectly consistent and make sense. When other situations, it might not be the case, and it would just be interesting to spell that out, these different contexts. And I think also about the phase averaging in Gibbs and statistical mechanics. I mean, Roman and I have done some work under which conditions you get actually the same values as in Boltzmann and equilibrium, so that the phase average in Gibbs, the Gibbsian phase average agrees with the Boltzmann and equilibrium value. But then you have some examples where this is not the case. And I think we have just done some, in a way, very simple basic theorems, but I think there's scope for further work. I'm sure there are other theorems out there, and they will be just interestingly, I think mathematically, I'm sure there are other theorems out there that relate phase average to Boltzmann and equilibrium values. So just to say, I think further work on that can be done, I think, and will be interesting. Maybe one more thing to say, emphasized it yesterday also, that we do have to be careful. I mean, these distinctions between Boltzmannian and Gibbsian statistical mechanics are, of course, introduced in a way by the literature, by us. And we have to be careful not to have debates about that there's only one version of Boltzmann and statistical mechanics, or there's only one version of Gibbs. I think that's not clear. You know, can of course be different versions of Gibbs. There can be different versions of Boltzmann. So this is what I mean by saying not essentialize these terms, not assume there's just one version of Gibbs. There can be different versions. It's fine. And yeah, maybe a final comment about what Jos has said about Boltzmann and the condition of that the number of particles or the number of elements is large. He's of course right about that many in the calculations Boltzmann does, and historically this is what is assumed. But it's not a but, it's just to point out that in the framework that Roman and I have developed, you can of course also apply that. What I introduced yesterday is the Boltzmann framework. It is of course very abstract. We have just these macro variables, macro values. You can also do that for systems that don't have extremely large n, but just a large n or medium large n. Yeah, it's just a small side comment. But to summarize, really, I think there's scope for further work, many interesting questions, and yeah, thanks. Thanks for the debate.
Thanks, Katie.
Hiya. Lovely to see you all. Sorry to miss you all online whilst the SPS has been happening here in Glasgow. But so I think I'm like everybody else largely in agreement with what's been said. I mean, I think the thing that I found when I was first thinking about these things that made me at first it feels like there's these two rival things, and then you think, okay, well, does there have to be like one true entropy to rule them all, or can we just like let 1,000 flowers bloom and have these different frameworks and see that they're kind of applicable in different places? And I think the comments that Jos and David have made about how you can kind of see how they can be similar and overlap in certain cases and not in other cases, I guess, like kind of it lends itself to saying, yes, okay, fine, we can just let we don't have to pick. Why do we have to pick one rather than the other? We can just let 1,000 flowers bloom. I guess the reason for thinking that maybe we can't, the kind of, I'm quite tempted by that thought. So my kind of best stab at thinking, no, we really should try and think of them still as being rivals. I think the best arguments for trying to keep them separate, things like Charlotte and Roman's work, where they say they give different predictions, that seems like a good reason to have to say, look, no, really, we have to keep these two things as being distinct. We've got to pick one thing rather than the other. Or the idea that we have like kind of different philosophical, there might be certain philosophical projects for which you have to pick one rather than the other. So for instance, I'm thinking that depending on your account of reduction, you might think that really, in order to think about what the kind of microphysical basis of the thermodynamic entropy is, you've got to pick one thing rather than the other. You know, there are accounts of reduction that are maybe kind of happy with there being lots of different possible realizers, but there, you know, for some people that's going to involve forcing a choice. So I guess that's another avenue for pushing this idea that we shouldn't just be kind of liberal in the way that I feel quite tempted to be. And I guess the final reason to push back against this let 1,000 flowers bloom kind of idea would be, and this comes back to what David said about the, you know, Goldstein saying that kind of scientific practice is wrong, is you might think that there's different avenues, and this is kind of echoing Eugene as well, that it depends on what you think, like where we should put our efforts, you know? So I think there's all these conceptual problems, and we might be, you know, Goldstein's motivated by these philosophical concerns about probability and things like that. But you might think, well, actually, you know, it's really fruitful to try and think about small systems, and lots of kind of work now is happening on quantum cases. And so that might be, again, a reason to be a little bit less liberal, perhaps, in letting all these different projects coincide. 'Cause you might think, well, really, we're going to get a lot more interesting new results by following the kind of quantum Gibbs direction. Though I kind of think that the people who want to go down that line can still be very happy with more work continuing in the Boltzmannian tradition as well. So yeah, I think it's tempting just to say, no, we don't need to have one entropy to rule them all. We can be a bit more liberal. But I guess that those are the reasons that we've all discussed together that I think might push us against that.
Thank you. Any comments or questions from the audience before we go back to our panel? Yeah.
Thanks a lot. First, I just wanted to a little disclaimer that I'm actually just a first-year PhD student at theoretical physics, so it's kind of a very different kind of language that you use and an approach that you have towards the questions, fundamental questions in physics, that I find really interesting and enriching, and I think that conversations between theoretical physics in thermodynamics and in philosophy of physics should be more active, because I think that we are concerned with questions that have huge overlap. And well, the disclaimer is that I don't have like the training that you have in regards to argumentation, so maybe it's going to be difficult for me to communicate my ideas in that sense. And I feel very fortunate to have been in this conference and to know all of you and to see how you do philosophy of science. So first, just wanted to say that I'm very sympathetic with Eugene's perspective about more like contextually driven towards either one of the Gibbsian or Boltzmannian interpretations or approaches to thermodynamics, because as you say, there are many contexts where the Boltzmannian approach doesn't really make that much sense, and I think that Bixin example shows that very clearly, that if you go out of certain assumptions about the strength of the interactions between the systems, then I'm not sure where it breaks down, but my intuition tells me that's correct. I guess there is a problem maybe identifying what the microstate is or something of the sort that doesn't allow you to identify this large region of the of macrostates where the state is going to lie in the long term. So I think that that's a fundamental issue that maybe these Boltzmannian approaches may have. So something that is stick in my mind is this reluctancy, maybe, but I'm not sure whether this is true, of the Boltzmannian approach to use probabilistic descriptions in their formalism, because for me it sounds very like an easy way to get a probabilistic description. If I get any continuity equation and I normalize that, if I have a current of mass and a density of mass, and I write a continuity equation for that, and I divide over the total mass, I can prove mathematically that this is going to be a good probability density. And I can do that with electrons. I can do that even with probability in quantum mechanics. I can find a continuity equation and talk in these terms. So I think that why is there like that resistance towards assuming that interpretation is it, because of the ontological problems that probabilistic interpretations have, or is this a reluctance or a resistance towards assuming maybe a more epistemic approach to the descriptions?
This is pretty about the use of probability formalisms. So the Boltzmannian system mechanics defenders, they are the people who also prove those theorems with probability distributions and probability flows and continuity equations. And they use them to formulate their typicality assumptions with typicality results. So it's not that they resist using probability in a formalism or theory, but it's really like getting to the foundational questions. What is the theory? What is the result ultimately about? And I still get sometimes confused when I hear objections like, you cannot apply Boltzmann system mechanics to this example or that case. Insofar as the Gibbsian distribution is a property distribution over some kind of microstates, then there's going to be an easy way to translate that into some kind of Boltzmannian language about typicalities over each conditions or typicality over trajectories. So it should be relatively easy to translate back and forth between Gibbsian and Boltzmannian system mechanics. Of course, maybe there are some way translation is not good, but if we think about coarse graining as the thing we do in both Gibbsian and Boltzmann system mechanics, then it's pretty common technique we use. So it should be the common tool to kind of get a Gibbsian interpretation or Boltzmannian interpretation.
Yeah. So everyone's being very emollient and pluralist and conciliatory. I want to carry on fighting. And let me make two comments about picking up what was said. So the first one sort of comes to Eddy's comment about typicality, and I think that I suppose in a sense this comment is conciliatory. But so if you look again at Shelley's paper, it comes in 4 parts. I'm just using this because I think it's extremely clear and extremely influential, so it's a good placeholder for at least however a large chunk of the community this is understood. The first part of that is introductory. The second and longest part is engaged with the detailed statistical mechanics, and I'll come back in a moment to it. Then the third engages with cosmology, and the fourth discusses typicality. There's a project in Shelley's paper about use of typicality notions to explicate notions of probability that I think is largely a project in the metaphysics of probability as applied to statistical mechanics. It's largely disconnectable from what's in the first part of Shelley's paper. Insofar as we want to use the term Boltzmann statistical mechanics to refer to that project, I'm pretty relaxed about that. I mean, for independent reasons, I'm not a supporter of that project, but I think it's largely transparent to the practice of statistical mechanics how that works. So that's the qualifier. But that's not what Shelley is talking about in the early part of the paper. It's not what Ray Callan is talking about. It's not what Maudlin is talking about in his review of SLA. That's a framework where we're saying we should abjure the connection of information and entropy. We should reject the idea that mixing technologies are anything to do with understanding the approach to equilibrium. This is the context in which we're saying things like, this abuse of mixing is so obviously wrong-headed that one can't help wondering about source fusion. We're not talking, in terms of how the term has been used and engaged in the philosophy literature for the last 30 years, we're not talking about the advocacy of a certain set of techniques involving macrostate partitions in the discussion of certain niche but important cases. And we're not talking about the explanatory power of the fact that in some substantially significant cases, dispersions are small because there's an enormous variation in macrostate volume. That's not what's being pushed here. What's being pushed here is a motivated, in the good sense, just, legitimated, argued for, systematic critique of the practice of statistical mechanics in mainstream physics, which, if adopted, would involve rejecting large chunks of that as something we should stop doing. And it's a proposed replacement of that project with an alternative way of doing things. Go back to Craig's point about, we should need to do more work there. It's structurally extremely similar to the Boolean critique of mainstream quantum mechanics. It's coming from exactly the same people, and it has exactly the same flaw, which is not empirically adequate.
Excuse me? I thought one thing one could say in favor of Bohmian interpretation of quantum mechanics is that it's empirically equivalent to the ordinary Copenhagen type interpretation. And so if one is not empirically adequate, then the other isn't either.
Calculate magnetic moment of the electron to one board and get back to me. So yeah, sure. Look, it remains parallel. It's a good point. I shouldn't be so facetious. The bone theory is fine in an extremely narrow subdomain of non-relativistic quantum mechanics. Okay. And the Boltzmann theory is fine in a wider but still extremely restricted domain of statistical mechanics. Yeah. In both cases, those theories are silent in huge swathes of application. And it's not unreasonable to say, well, not many people working on this, we'll get back to that. That's a legitimate research. Sure. But Newtonian gravity is not empirically adequate, not empirically equivalent to general relativity. No. Just because it's
Okay. I agree with that. I mean, yes, I'm not sure if it's my turn to talk.
Yeah, it seems to be a discussion between the two of you. Why don't you say something, but then Bixin wants to say that.
Yeah, sure. I mean, what was I going to say? I agree that, well, first of all, when it comes to the prohibition on using mixing, what I remember from those days and what Shelley was talking about, he seems to claim that the microstate of a system would evolve to this overwhelmingly large subset, regardless of any assumptions about its dynamics, He rejects ergodicity, he rejects mixing. He said it would be ridiculous if it didn't move there. But you can't make a claim about how systems evolve without having some assumptions about its dynamics. It's not just that a set is so overwhelmingly large that the system must go into there. I mean, I put the objection against him once, like, look at the actual trajectory of the microstate to phase space. It's a path of dimension 1. It's a subset of measure 0 in the entire phase space. Now look at the set of all the points that the state doesn't visit in its trajectory through time. It's a set of measure 1 and is completely dominant in phase space. So, can we conclude just from comparing the measures of those two sets that the system must inevitably be moving into the set of systems that it never visits? This, of course, is absurd. So there must be something more to say about how the system evolves. And you can reject mixing if you like, but then you have to come up with an alternative. And that is not something that I've seen I've seen a proposal for. A second thing is, yes, I mean, this case, the class of problems that seems to be have a reasonably developed approach from a Boltzmannian perspective seems to be pretty small. For example, I don't know of, you can apply Boltzmannian approaches to magnets, sure, or special other cases, but is there a Boltzmannian treatment of, say, phase transitions and criticality? I don't know of one.
I'm skeptical because fluctuations are large.
Yeah, well, so yeah, but does he do that using a Boltzmannian approach, a strictly Boltzmannian approach? Well, just in sense of characterizing phase transitions and equilibration. Well, I'll look that up. That's a good idea.
I also want to start a fight. I want to remind just how the debate has been carried. There are actually two related but distinct questions in the field. One is about the foundations of statistical mechanics. Suppose we want to systematize or even axiomatize statistical mechanics. What is the right way to do it? And the other question is the more philosophical, conceptual questions like, how do we understand why systems tend to approach equilibrium? And even questions about why there's direction of time. I think there's a track of the Boltzmannian started with the second kind of question, the more conceptual question. And to add on what David said earlier, although it is true, the standard tool in physics is the Gibbsian. But if you ask the conceptual questions about why is there direction of time, they're going to more or less give a Boltzmannian answer. And if you push them about, oh, what about the Gibbsian thing? And their first reaction was like, oh, isn't Gibbs entropy invariant in time? So I do think there's a sense that there's two separate questions, and we're sort of trying to answer them at the same time. And of course, I think the Gibbsian has the answer to the more conceptual questions, but that's less studied, or even just less acknowledged by the community compared to the Boltzmannian answer. Yeah, I just thought keep these two questions in mind. At least separate may help us to see, like the Boltzmannian has the issue, they want to generalize, like they had some conceptual answers to the question about second law, about the direction of time, with some specific cases like ideal gas. Then they're facing the problem, how are they going to generalize their cases to broader, because it is a fundamental question in the sense that like so many systems equilibrate, they can't just do some cases. On the other hand, although Gibbsian approach is widely practiced, but it still need developed to address those conceptual questions more appropriately.
Charlotte, go ahead.
Yeah, great. Thanks so much. I mean, this is really just a comment on what Jos said, and about the condition of mixing is, of course, extremely strong, but the typicality proponents need, I agree with Jos, of course, that I mean, the system has a dynamics, so in a way, you can't escape saying something on the dynamics. And I don't want to promote our work, but I mean, I just want to say that it would be nice to have more discussion. I mean, I have together with Roman, we have that paper where, you know, where we set out necessary and sufficient conditions for equilibrium to exist. It means you actually structurally know what conditions you need for a system to have an equilibrium. I mean, what dynamical conditions you need for systems to having an equilibrium, namely the phase space or state space, you know, your space of all possible microstates, has I mean, each dynamical system also, so each also your gas or other statistical mechanical system governed by Hamiltonian dynamics can be broken up in ergodic components. So there are always components that can be of measure zero, but a system can be broken up into components, and then you actually know for an equilibrium to exist, you have necessary and sufficient condition. Namely, when does it exist? Well, when the dynamics is such that each of these ergodic components, the equilibrium region is the largest macro region. And so you actually know from that kind of characterization how the dynamics has to look like for an equilibrium to exist. And it would be nice to have the typicality proponents engage a bit with that. Yeah, I mean, just not necessarily with our paper, but yeah, just with the dynamical conditions, because you can actually characterize what you need. And so and what you need is, of course, much weaker than ergodicity, much weaker than mixing. It would be nice if they engaged a bit in that. It's all side remark to what Jos has said. Thanks.
Eddy, do you have something to add to? Okay. Actually, I have a comment about this approach to equilibrium thing, because I think there's been sort of an interesting dialectic that went on with this. So there's a deceptively simple pseudo explanation of equilibrium, which is entirely in terms of the geometry of phase space. The equilibrium macro state is just so much bigger. How could it not go into it? And there's a lot of what these Boltzmannians have said suggests that you can give an explanation of equilibration entirely divorced from dynamics, right? And including what Shelley says in that paper that David's quoting. But I remember a number of years ago, there was a conference in Jerusalem. I think you were there, Jos. Where Roman gave a talk which became the basis for his critique of the typicality approach to equilibrium. And Shelley was out there, and he basically Roman was criticizing the view that you can talk about explain equilibration without any references to the dynamics. And Shelley was there, and he objected and said, no, actually, I do think the dynamics play a role. And in that, I think it's in the paper David was quoting when he says something like, the equilibrium macrostate is just so big that unless the dynamics are ridiculously special, it'll quickly move to the equilibrium macrostate and stay there for a long time. And in conversation, at least with Roman after that talk, what Shelley said was, okay, what I meant was that there are results to the effect that typical Hamiltonians are ergodic. So take a non-ergodic Hamiltonian, you perturb it a little bit, and it's ergodic, and so that's what I meant by saying it's only ridiculously special Hamiltonians that would keep you from equilibrium. Now, how do you reconcile that with railing against mixing? That's a good
And ergodicity.
and ergodicity. That's a good question, right?
Yeah.
But I think that, I mean, it's certainly true that I think it is more or less non-controversial that questions about equilibration cannot be divorced from questions of dynamics. And if the Boltzmannians aren't assuming ergodicity or mixing, it is fair to ask, well, what are you assuming? And on this question of equilibration, I'm going to get conciliatory again, because the ranting against the use of Gibbs entropy in the Boltzmannian has to do with its inappropriateness as a measure to track equilibration, progress to equilibrium. Because for an isolated system, it doesn't change. Well, what I said in my talk was basically, well, if you want a concept of entropy that has the same relation to available energy that thermodynamic entropy does, then the Gibbs von Neumann entropy fills the bill. And I said that I've given similar talks with Tim Maudlin in the audience, and he didn't object. And and I know that David Albert, right, exactly. And I know that David Albert says, okay, yeah, if you're thinking about thermodynamics as a resource theory, then it's perfectly okay to have a entropy that's relativized to a state of information. And what I was not claiming is that this entropy is a useful thing for tracking progress towards equilibrium. And in fact, I would just all get away from the idea that that's what entropies are supposed to do. Because if you look at actual studies of equilibration in these days, it's almost entirely in the quantum context, for good reason, right? The one I'm most familiar with is the Linden, Popescu, Short, and Venter result, and it's an equilibration result. And what they're using to track progress to equilibrium is trace distance between the density matrix and the equilibrium one. It's not entropy. It doesn't have to be. And I think that if you look at other studies of equilibration, okay, sometimes an entropy is a useful thing to track progress to equilibrium. Sometimes it's not. People are very opportunistic. They tend to use whatever it is that they can prove theorems about. And I think that if we get away from the idea that that's the primary role of entropy is to track progress to equilibrium, then I think a lot of the force of some of these polemics sort of dissolves.
Well, I don't need a microphone, but I want to respond to that. Because this is closely related, of course, to Boltzmann's work on the Boltzmann equation and the H theorem. So Boltzmann shows there is this quantity which we can abstractly call H, which has a monotonic behavior in the course of time. And then a few pages later, he says, oh, this is actually entropy. He identifies it all with minus entropy and says, I have proved the second law of thermodynamics. Now that, I said, is a fairly optimistic conclusion, and he's jumping ahead of himself. Because if you want to talk about thermodynamic entropy, as we all have learned from various talks, It is a state function. It's a function of equilibrium states. Thermodynamics associates entropy only to equilibrium states. The evolving distribution function in the course of time is not in an equilibrium state. So what Boltzmann is doing is actually proposing an extension of the previous concept of entropy that is now also defined for non-equilibrium states, and he still calls that entropy. And if you accept that kind of thinking, then suddenly it becomes you create a second role for entropy beyond the usual thermodynamical meaning of entropy, that it should also track the progress of equilibration. And that's one of the reasons why we introduced this minus first law, is to say that you can talk about equilibration without having to talk about entropy. And so if you look at Gibbs's entropy and say, oh, it's constant in time, so it doesn't track equilibration. Yeah, that's right. But Gibbs entropy was not meant to track progress to equilibration. That's something that is typical for Boltzmann's thinking. So you're asking a question that is, I think, inappropriate in the Gibbsian framework. If you say, or are you raising an objection? If you say, oh, the Gibbs entropy is invariant under time, so it's no good for tracking equilibration. Well, it wasn't meant for that purpose.
You can add your next one.
Okay.
Right.
And I would also say neither is the Boltzmann entropy, because the equivalent of Boltzmann entropy in the quantum context is the dimension of a subspace. And that would be great if we could count on states to go into some macro state, to go into a state which has support on some macro state, but they don't, right? Right. So, I mean, it is important for these kinds of discussions that for systems with many degrees of freedom, there will be a macro state that of very high dimension compared to other macro states. But if we're trying to use the Boltzmann entropy of the macro state that the state is in, typically there will be no subspace larger than the whole space to track entropy.
I have a quick comment on this. Yeah, so you're right that if you think about the quantum Boltzmann entropy of the wave function or density matrix, it can be a superposition of various macro states. This is because quantum theory, you have this kind of dispersion in different macro states. But in the when you resolve the measurement problem, like in collapse theory or many worlds or Bohm, you have other things to plug into the entropy function. You have the effective entropy, just like you have effective energy, effective this and that quantum properties. So in that case, you can still track the quantum Boltzmann entropy in terms of the quantum state and say the local variables or something else like the branches of the wave function.
Sometimes will go down.
Sorry?
And sometimes will go down.
Sometimes it goes down, but typically it goes up. And that's what we want to prove is the Shorty equilibrium from that kind of quantum Boltzmann entropy plus the information about the solution to the measurement problem.
Yeah, I mean, it's not directly to that. It's back to, well, I want to come back to Bixin's point in a moment. Let me just comment on the engage here. I mean, here's a qualifier to this kind of move against entropy. I mean, so I agree. If we're interested in the general question of equilibration, most of that is being studied in quantum mechanics, and entropy is not, in fact, a terribly useful distance tracker. If we're interested in equilibration in particular systems, and in particular if we're in a local thermodynamic equilibrium regime, which is where a huge amount of this is done, there I want to defend the fact that entropy is just really important and useful, and it really matters in analysing, viscous fluid dynamics or stellar structure formation or something that I've got this quantity entropy. I can think of it as defined in local thermodynamic framework. So it really like it bridges the non-equilibrium object and the equilibrium object because its numerical value at a given point is calculated from the equation of state equilibrium. But it is non-decreasing, and it is locally non-decreasing. It can't decrease here and increase right up here unless there's a long-range interaction. So that's, I mean, I don't know what the historical aspect of here, but that is a place where I think it's relevant to think that there's an object that is bridging the thermodynamic entropy and some tracker of systems evolution towards, well, even if even if something like the sun that isn't evolving towards a global equilibrium state, it's still evolving while the distribution is increasing. I mean, going back to Bixin's point, I think is important. So one thing I think here's a concession to that matters. So a part of the story we haven't talked about is you do have extremely influential people in physics writing very influential semi-popular books, Roger Penrose, a decade later Sean Carroll, which absolutely are using a Boltzmannian conception of entropy and a past hypothesis type story about equilibration. So that's certainly in the mix, I agree with that. I want to push back a bit against the idea that the Boltzmannians are thinking about this question, the Gibbsians aren't. So if we use Boltzmannians in the way I said, then as the advocates of this particular revisionist program, critical program in philosophy of statistical mechanics, they're absolutely very concerned about equilibration and about the hour of time. I agree. If Gibbsians then means like everyone else in that neck, then sure, the vast majority of them are concerned about the hour of time, just like the vast majority of people were doing solid state physics aren't really a measurement problem. But that's unsurprising, that's just a structure there. It isn't true that there aren't lots of people in non-equilibrium stat neck who write about the hour of time. If we're talking by Gibbsians, we mean people in philosophy of physics who've advocated Gibbsian theorem. I don't think it's true. I mean, there aren't that many people who've done that. And advocated a solution from the time that's direction of time that's actually pretty resilient with the Boltzmannian approach. The idea that cosmological data is relevant, right or wrong, can be separated out from the Boltzmannian framework. But the other thing I say about the hour of time question is, if you look at the tradition in non-equilibrium stat neck about talking about hour of time, normally the chapter on the hour of time is the last chapter in a monograph about non-equilibrium statistical mechanics. And there's kind of a good argument for that, which goes something like, the thing you want to explain is why all the equations you managed to derive from microphysics run in the same direction and are irreversible. And there's at least a way of getting at this problem where you can't answer that question until you've actually discussed how to derive the equations. So I think this goes a little bit to my comment on your talk, on the search between Boltzmann's criticism on the talk. I mean, we can't separate out our supposed qualitative explanation from of the reason why youth passes and coffee cools from the question of how to justify in detail the actual derivation of the myriad irreversible mesodynamic equations we use.
I don't disagree, but
Not really intense disagreement.
Maybe, I guess this is just an observation, similar to the quantum mechanics case. There may be, I don't know, heuristics or easy to communicate to the public in terms of, or closer to our intuition, going with the Boltzmannian/Bohmian kind of story. Again, not defending it, but just observing there's a pattern in terms of how to tell the story.
But being intuitive and being explicable to the public are necessary but not sufficient conditions of good popular science being true is also
Have we actually reached a point where people don't have anything, they feel like they urgently have to add?
I can go until Pascal, but I think I said it now.
Okay, then, okay, thank you, everyone. This has been a really stimulating discussion for me, and thank you for our participants across the ponds, or actually, not, I guess, across two oceans. And thank you, everyone. Thank you for the audience.